In this video we're going to look at sequences. So what I want you to do is consider these sets of sequences. This is a set of numbers. This is one here, and here's another set here. Now each of these numbers has a rule to find the next number in each of the terms. Anything that follows a pattern is called a sequence, and we're going to look at sequences in a particular type called a recurrence sequence. Let's look at the notation first of all. There are n numbers in this sequence. So the number in the sequence is the nth number. Each of these is called a term. So this is the first term, and we use the letter T to define terms. This is term number 1, T1. This is term number 2, T2. So on, term number 3, and so on, term number 4. And obviously the sequence continues. If we're looking at a general overview, we'd say that Tn is the number of terms in any particular sequence. So let's look at recurrence sequences. So what that means is that you're using the first term to find the next term. Then you use the next term plus a rule to find the term after, and so on. You can find subsequent terms in the sequence. So let's do an example. Let's find the first 4 terms. So we're finding the first 4 terms of a recurrence relation where we add 5 each time. Sometimes recurrent has other names called iterative. You may have heard of an iterative sequence. So if we're adding 5 each time, so our rule is add 5. Now the notation that we use, we say, well, term 1. Okay, term 1 we have to be given. So let's say term 1 is 3. The first term is 3, and we're going to find the first 4 terms. So term 2 will be found by adding 5. So term 2 becomes 8. Term 3, well, we take the previous term, 8, and then we add 5. So that third term becomes 13. And term 4, we take the previous term, 13, and we add 5, which gives us 18. This is a recurrence sequence because it's dependent on the term before to then find the next term. It's also useful to realise that if Tn is one term, then the term before it we can say is Tn minus 1. So this notation is really useful with recurrence relationships. I can write the 5th term, T5, as T to the n minus 1 plus 5. Okay, so obviously that would be 18 plus the 5, which would give me the next number in the sequence. What we need to be able to do is generate some sequences from a rule. So Tn is the notation that finds the term number, and this is the rule in terms of the term number. So we need to find the first 4 terms. So let's let n equal 1 first of all. So that tells us that we're finding term 1. Well, if n equals 1, it's 2 times 1, following the rule above. 2 times 1 is 2. So the first term of the sequence is 2. Let's find the second term. The second term is 2 times 2, which is 4. So our second term is 4. The third term is 2 times 3, 6. And the fourth term is 2 times 4, which is 8. Now we have the first 4 terms are 2, 4, 6, 8, using this rule. Let's look at this one. This time we're trying to find the terms with the rule 2 to the power n minus 1. So we're going to find the first 4 terms. So let's let n equal 1, 2, 3, and 4. So when n equals 1, we're looking for the first term. Following the rule and subbing that in, it's 2 to the power of 1 minus 1, which is 2 to the power 0. 2 to the power 0 is 1. So the first term of the sequence is 1. Let's look at the second term of the sequence. 2 to the power of 2 minus 1, which is 2 to the power 1, which is 2. Third term, let's let n equal 3. 2 to the 3 minus 1, which is 2 to the power 2, which is 4. And finally the fourth term, which is 2 to the power of 4 minus 1, which is 2 to the power 3, 8. So our first 4 terms of this sequence are 1, 2, 4, and 8. Finally, let's look at this one. This rule is 2n minus 3. So if we're subbing in n equals 1, that's the first term. 2 times 1 minus 3 is 2 minus 3, which is minus 1. The second term is 2 times 2 minus 3, so 4 minus 3, which is 1. And the third term, 2 times 3 minus the 3, 6 minus 3 is 3, and finally the fourth term, which is 2 times 4 minus the 3, 8 minus 3 is 5. All right. You also need to be able to find the rule from a sequence, and sometimes the rule is obvious. For example, we can recognize a set of numbers such as the 2 times table, and we know that if we're going from the first term to the second term to the third term to the fourth term, we're adding 2 each time. Well, that tells us that to go from n, the term number, to the actual number in the sequence, we multiply by 2. So the difference between the numbers in the sequence tells us a lot about the rule. It tells us that if it's a common difference or a constant number, that helps us to identify the rule. So we can say that the general rule for this sequence is 2n. The common difference does help us. If you look for a common difference and it's not a constant number, you then look at the second difference, and that might identify what kind of sequence it is. If it's a common difference straight away, and it's constant, that means it's a linear progression. So let's just do one where we've got a sequence of numbers. So I'm going to go minus 4, minus 1, 2, and 5. Okay, now we've got 4 numbers in the sequence here: first term, second term, third term, and fourth term. So I often set up a little table, the term number, and we've got 1, 2, 3, 4, and here's the number in the term. And we've got the common difference here. Each time is 3. So every time it's plus 3. Now, because it's a constant number straight away, when we look at the common difference, it must be a linear. And this tells us that we're going to go 1 times 3 to get to this. And then we have to work out if there's anything else we have to perform. So the term rule is going to be 3 times n. So 1 times 3 is 3. We have to add 7 to get to negative 4. Let's check the rule works for all of these. 3 times 3 is 9. Add 7. Sorry, what I'm saying. Yeah, 3 times 3 is 9. Add 7. Incorrect. Must be take away 7. It's just me being silly and not thinking properly. Let's try again. Sorry. 1 times 3 is 3. Take away 7, which I think I said. So 3 times 3 is 9. Take away the 7 gives me back to 2. 4 times 3 is 12. Take away the 7 gives me back to 5. Alright, now what happens when the common difference is not constant? So let's look at this sequence of numbers. Now again, you might be familiar with this sequence of numbers. Hopefully you recognise that sequence of numbers, but look at the common difference between each of the terms. It's not a constant number. This is plus 3, this is plus 5, and this is plus 7 between each of the term numbers. So obviously n is first term, second term, third term, and fourth term, and there's the term in the sequence. Well, because it's not a constant, we then go to the second difference. The second difference tells us that it's gone up a power, so it's no longer a linear sequence, it must be a quadratic. If we go to the second difference and we get a constant, and we can see it is a constant, look now, it's plus 2 every time, that tells us it must be a quadratic sequence. Third difference must be a cubic sequence. We don't study these in maths methods though. So having a look at this, we've got the fact that these are all square numbers. So therefore our general rule for this equation, or this sequence, apologies, is Tn equals n squared. And we don't need to add anything. So if it was 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, and so on.